When we think about the universe, we naturally ask, how did everything start? This inquiry took me on a journey through the realms of astrophysics and cosmology, seeking answers to the very essence of existence. At the most basic level, we still don't know how or why the entire universe came into existence. Indeed, we try to figure out why things are the way they are. Approximately 13.8 billion years ago, the universe came into existence. But we don't know how this happened. It then rapidly expanded, leading to the formation of matter and the universe as we know it. Just how this is possible is the biggest question in all of science. It involves going beyond the limits of theories and experiments, spanning the fields of physics and philosophy. This is the biggest puzzle in all of science. One moment, there was absolutely nothing, and then, all of a sudden, everything came into existence. This is the story of the beginning of our universe and what happened after that. As we travel into the past, nearly 13.8 billion years ago, we reach a moment known as the Big Bang singularity, where the universe is thought to have originated. Singularities are points where the curvature of space-time becomes infinitely large and, at the same time, the density also becomes infinitely high. Einstein's general theory of relativity predicts the existence of these singularities. According to this theory, space and time themselves started at the Big Bang. Before time, there couldn't be space, so there wouldn't be a universe. Searching for something beyond the origin of the universe is akin to trying to find a point higher than the peak of Mount Everest, the tallest mountain on Earth. There is no higher point to explore once you reach the summit. As suggested by renowned cosmologist Stephen Hawking, there might have been truly nothing before the universe's inception. When we discuss the behavior of matter near singularities, inside black holes, or at the Big Bang, quantum mechanics becomes relevant. Quantum effects, at extremely high energies and small scales, have the potential to alter the predictions made by general relativity. Stephen Hawking's groundbreaking work introduced the concept of Hawking radiation, which suggests that black holes can emit radiation due to quantum effects near the event horizon. Over time, this radiation causes black holes to lose mass and energy, leading to their potential evaporation. If this holds true, it raises questions about the ultimate fate of black hole singularities. Similarly, in the extremely early universe, when energy densities were incredibly high, quantum effects may have played a significant role. These are the two best-known theories that attempt to explain different aspects of the universe. General relativity is a theory of gravity that works well at large scales, but does not incorporate the principles of quantum mechanics. On the other hand, quantum mechanics successfully describes the behavior of particles on very small scales, but does not include gravity. Consequently, at the Planck scale, both theories break down, and we need a theory of quantum gravity to understand what happens. Some theories suggest that the universe may have had a singularity at the Big Bang, while others propose a cyclic model where the universe undergoes repeated cycles of expansion and contraction. As of now, our universe's origin story remains a mystery. Nevertheless, it's undeniable that 13.8 billion years ago, the universe started its journey. Back then, everything within the universe existed as a single Planck unit of time with a diameter of a single Planck length. The Planck length is the tiniest unit of distance, around 1.6 times 10 to the power of -35 meters, significantly smaller than a proton. To put this scale into perspective, the Planck length is about 100 million trillion times smaller than the size of a proton. And the Planck time is how long it takes for light to travel this super small distance in a vacuum, which is roughly 5.39 times 10 to the power of -44 seconds. Within this exceptionally confined space, the temperature of the entire cosmos reached the Planck temperature, an upper limit known as the absolute hot, approximately 1.4 times 10 to the power of 32 Kelvin. This temperature signifies the maximum limit at which particles can exist before their own energy breaks them apart. Conversely, there exists a contrasting extreme known as absolute zero. This corresponds to 0 Kelvin. At absolute zero, which is theoretically the lowest temperature possible, all the particles in a system do reach a state of minimal energy. However, they do not completely stop moving. This is because of a principle in quantum mechanics known as the Heisenberg uncertainty principle. According to this principle, you cannot simultaneously know the exact position and momentum of a particle. So, even at absolute zero, particles still have a certain minimal intrinsic energy, the zero-point energy. This energy results from the wave-like nature of particles, which requires them to be in constant motion. Going back to our story, the moment known as absolute hot occurs just a tiny fraction of a second after the Big Bang. This brief period, 100 million trillionths of a second, is termed the Planck epoch. In other words, after traveling almost 13.8 billion years into the past, we arrive at the Planck epoch. According to the Big Bang theory, the universe originates from a state of infinite density and temperature, often depicted as a sea of virtual particles or a false vacuum. The dynamics of this early universe are believed to be governed by a quantum theory of gravity or a comprehensive theory of everything that unifies all fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. During this time, the familiar rules of physics might not have been operating as we know them. At this point, all matter and energy are concentrated in a minute hot, dense singularity, a billionth the size of a nuclear particle. All four fundamental forces of the universe were unified into one single force. Theories suggest the emergence of WIMPs, weakly interacting massive particles, dark matter, and dark energy, potentially influencing the singularity's expansion. The early universe expands, gradually cooling, and initially appears nearly smooth, with quantum variations causing slight density variations. However, details about this era are limited due to the lack of effective means to test events so early in space-time, and we also lack a comprehensive theory. After just 100 million trillionths of a second, the extensive unpredictability of the Planck era ends. The universe then experiences gradual expansion and cooling, signaling the beginning of a new epoch known as the Grand Unification Epoch. During this Grand Unification Epoch, the universe is still infinitesimally small, hot, and dense. All fundamental forces were present and potentially unified at extremely high energy levels in the early universe. The temperature of the universe cooled down significantly to a temperature of 10 to the power of 32 Kelvin. Gravity is believed to have separated from the other fundamental forces and exerted its influence on the universe independently, while the remaining forces underwent a process of stabilization, merging into what is known as the electro-strong force. This force is alternatively called the Grand Unified Force. Scientists propose that the electro-strong force involves hypothetical particles called X and Y bosons. These particles mediate the interactions within the force. The presence of X and Y bosons allows early matter during this epoch to fluctuate between baryon and lepton states. At higher temperatures, the weak nuclear force and electromagnetism merge into the electroweak force. Expanding on this, as temperatures rise further, the strong force unifies, giving rise to the electro-strong force during Grand Unification. Extending this concept, at extremely high energy levels, all fundamental forces become a single unified force in Planck time. It has been experimentally verified, using particle accelerators, that electromagnetism and the weak force merge into the electroweak force. However, unifying the strong force with the electroweak requires much higher energies, surpassing even the powerful phenomena produced by events like supernovas and black hole jets. Additionally, a theory of everything is needed for a clearer understanding. Currently, due to the absence of a consistent theory and technological limitations, all these aspects remain unresolved. Nevertheless, the Grand Unification theory explains the state of the universe immediately following the Planck era. The Grand Unification Epoch lasts over 10 million times longer than the entire Planck era. At the end of this period, the entire cosmos retained a size smaller than that of a single quark, which is the smallest known particle of matter today. Around 1 trillionth of a second after the Big Bang, the universe entered the electroweak epoch. The temperature has reached around 10,000 trillion degrees. Due to a decrease in temperature, the electro-strong force undergoes a significant change, splitting into two distinct forces: the electroweak force and the strong nuclear force. As a result, the strong nuclear force fuels the inflation of the universe. However, the temperature remained high enough for electromagnetism and the weak interaction to remain merged into a single electroweak interaction. The decay of X and Y bosons gives rise to a diverse range of exotic elementary particles, including W and Z bosons. as well as Higgs bosons. However, these theories explain particle behavior after the Big Bang, but face challenges in detailing the formation of the large-scale cosmos. Following the electroweak epoch, the inflationary epoch begins 1 billion trillion trillionths of a second after the Big Bang. The temperature has significantly decreased by around 10 billion trillion degrees. During this rapid inflationary period, the universe doubles in size around 90 times, within a time frame of less than a trillionth of a second. In simpler terms, the cosmos undergoes a volumetric expansion of at least 10 to the power of 78, corresponding to a linear growth of at least 10 to the power of 26 times in every spatial dimension. To put it into perspective, an object initially 1 nanometer in length, about half the width of a DNA molecule, would expand to approximately 10.6 light years, 100 trillion kilometers, in length in just a tiny fraction of a second. This phase of the history of cosmic expansion is known as inflation. Inflation offers an explanation for certain characteristics observed in our universe. What causes the expansion of our universe? Why does our universe look the way it does? Why does the universe appear uniform in all directions? How can points over 13.8 billion light-years apart average their distance without violating the speed of light? Why is the universe flat? Additionally, why is the universe seemingly uniform? And why haven't magnetic monopoles been observed? While electrical charges cancel each other out in positive and negative pairs, magnets have both poles. However, isolated magnetic poles, similar to isolated charges, appear to be non-existent. These cosmic mysteries challenge our understanding of the universe. Alan Guth proposed a remarkable solution to all of these problems. The solution comes from the concept of inflation. Inflation is what put the bang in the Big Bang. In less than a trillionth of a second, the universe exponentially inflates, addressing these problems. This rapid inflation also addressed missing magnetic monopoles, horizons, and flatness problems. Firstly, the horizon problem. The horizon problem is a question about the surprising homogeneity of the universe. Despite the fact that causally disconnected regions of the universe have the same temperature, they should not have been able to exchange energy or information due to the constraints of the speed of light. This is what makes the observed uniformity of the cosmic microwave background radiation across the sky a puzzle. Inflation theory provides a solution to this problem. It proposes that the early universe went through a phase of exponential expansion, which stretched quantum fluctuations to macroscopic scales. This means that regions of the universe that appear causally disconnected today were actually in close proximity before inflation. Therefore, these regions could have reached thermal equilibrium, explaining the observed homogeneity. Furthermore, our observable universe is just a small bubble within the entire cosmos. The regions beyond our observable universe could be vastly different. However, these regions are currently inaccessible to us due to the finite speed of light and the ongoing expansion of the universe. Secondly, there is the flatness problem. The flatness problem is a problem within the Big Bang model of the universe. It arises from the observation that the density of matter and energy in the universe is very close to a critical value. This critical value is required for a flat universe, and any departure from this total density would increase rapidly over cosmic time. To put it more scientifically, the flatness problem arises because we appear to live in a universe that has an observed density parameter very close to 1. In other words, the universe is very close to its critical density. For the universe to be so close to critical density after 13.8 billion years of expansion and evolution, it must have been even closer at earlier times. This seems like a truly remarkable coincidence and has become known as the flatness problem. There is no known reason for the density of the universe to be so close to the critical density, and this appears to be an unacceptably strange coincidence in the view of most astronomers. Lastly, there is the absence of magnetic monopoles. While we can find electric monopoles in the form of charged particles, we have never observed magnetic monopoles. Inflation provides a potential explanation for this absence by suggesting that if magnetic monopoles did exist, they would have been spread out during inflation, making them difficult to detect within our observable universe. The quantum fluctuations in the early universe were stretched by inflation. These tiny fluctuations were transformed into the large-scale structures observed today. The transformed quantum-scale irregularities became the seeds for the formation of large-scale structures in the universe, such as galaxies and galaxy clusters. High-density regions continuously attracted more matter from the surrounding space, and over time, these high-density regions collapsed into the large structures of the universe. The growth of structures is thought to be governed by mysterious dark matter, which constitutes about 85% of all matter in the universe. Cosmologists have dedicated decades to exploring the mechanisms behind inflation. Despite extensive research and proposed models, the exact mechanism or particle initiating inflation remains unknown. It's important to know that when we talk about the electroweak epoch in the early universe, it can be seen differently depending on the model scientists use. Some models suggest it started before the inflationary period. On the other hand, in different models, the electroweak epoch is said to begin after the inflationary period. According to traditional Big Bang theory, the exact end of the inflationary epoch is not precisely known, but it is estimated to have occurred between 1 billion trillion trillionth and 100 million trillion trillionth seconds after the Big Bang. The rapid expansion during inflation caused elementary particles from the Grand Unification Epoch to be distributed thinly across the universe. At the end of the inflationary epoch, the potential energy stored in the inflaton field was released through a process known as reheating. During reheating, the inflaton field decayed into other particles, repopulating the universe with a dense, hot mixture of quarks, antiquarks, and gluons. In inflationary models, inflation is thought to have been triggered by the separation of the strong nuclear force from the electroweak force. One theoretical consequence of the separation is the emergence of a scalar field known as the inflaton field. As the universe evolved, the inflaton field underwent a phase transition, settling into its lowest energy state throughout space. During this settling process, the inflaton field generated an enormous repulsive force. This force acted as a driving mechanism for the rapid expansion of the universe. This inflaton field is thought to have caused the universe to undergo a period of rapid expansion, forming a universe consistent with observed spatial isotropy and homogeneity. The decay of X-boson messenger particles, which carry the electro-strong force, is indeed theorized to have triggered strong inflation. This powerful inflation field is thought to be carried by a new messenger called the inflaton. However, it's important to note that the exact particle physics mechanism responsible for inflation is still unknown. In non-traditional inflationary models, although inflation may have ended around 100 million trillion trillionth seconds after the Big Bang, the observed homogeneity of the universe suggests that the duration of inflation must have been longer. Following the end of inflation, the universe continued to expand, but at a decelerating rate. Around 4 billion years ago, the expansion began to accelerate again, attributed to the dominance of dark energy in the universe's large-scale behavior. Cosmologists believe that in the early universe, everything was perfectly symmetric. To maintain symmetry in the fundamental building blocks of the universe, scientists propose the existence of a hidden particle for every known particle, the concept known as supersymmetry. For every known particle, there could be a hidden partner particle, forming a kind of symmetry in the universe. However, if this symmetry exists in our universe, it must be broken at a high energy level. If supersymmetry breaks at a very high energy level, the masses of particles and their superpartners won't match, making it challenging for us to directly observe these hidden partners. That's why we haven't seen them yet. They might exist, but at energies that our current experiments can't reach. Particles created during the inflationary phase underwent thermalization. During this process, mutual interactions among particles led to thermal equilibrium. Exotic entities, known as sphalerons, were thought to exist. Sphalerons are configurations of gauge fields that violate the baryon and lepton numbers. As the universe's temperature dropped, electroweak symmetry breaking occurred. This has two interconnected consequences. 1. Through the Higgs mechanism, elementary particles interacting with the Higgs field acquire mass, having been massless at higher energy levels. 2. As a byproduct, the weak nuclear force and electromagnetic force, along with their respective bosons, the W and Z bosons and photons, begin to exhibit distinct behaviors in the present universe. Prior to electroweak symmetry breaking, these bosons were all massless and engaged in long-distance interactions. However, following this event, the W and Z bosons become massive particles, interacting only over distances smaller than the size of an atom, while the photon remains massless and retains its long-distance interaction capability. After electroweak symmetry breaking, approximately 10 to the power of -12 seconds after the Big Bang, we commenced in the quark epoch. At this point, the fundamental interactions of gravitation, electromagnetism, the strong interaction, and the weak interaction had their present forms. Everything follows the lead of four fundamental forces. Imagine you are in the living room. First, there's gravity, which keeps you on the couch. You then effortlessly lifted the TV remote. When you lift the TV remote, you're dealing with electromagnetism. Pressing a button sent invisible signals through the air, making pixels on the screen light up. These pixels revealed a world of images. Now, deep inside you, there's a strong force. It's like a super glue holding protons and neutrons together in atoms, making up everything in your body. On the subtle side, there's the weak force, which can cause tiny changes in atoms through processes like beta decay. All these forces combine to shape our experiences in the universe. Whether it's gravity on a large scale or the tiny forces inside atoms, they all play a part. If you're curious to learn more, there's this cool video about the fundamental forces of nature. And there's another one on particle physics. Check out the link in the description below. Back to our story. Despite the fundamental interactions taking their present forms, the universe's temperature remained too high for the stable formation of many particles we observe today. At this stage, there were no stable protons, neutrons, atoms, atomic nuclei, or molecules. Any composite particles that formed due to chance and interactions at these high energies would quickly break apart again. At the end of this epoch, the universe is filled with a hot quark gluon plasma. During this phase, quarks, leptons, matter, and antimatter coexist under the influence of gravity, the strong nuclear force, and the electroweak force. Despite this coexistence, the universe persists in a chaotic state until particles acquire mass through a subsequent energy drop and transformation. As temperatures and energies decrease, the universe undergoes a gradual transition. Additionally, baryogenesis is believed to have occurred around the same time frame of 10 to the power of -11 seconds. The asymmetry between baryons, such as protons and neutrons, and antibaryons in the universe is a significant puzzle in cosmology and particle physics. The expectation, based on certain principles, is that both baryons and antibaryons should have formed in equal quantities during the early stages of the universe. However, observations indicate a substantial excess of baryons over antibaryons, and almost no antibaryons are observed in nature. This lack of antibaryons in the observable universe is known as the baryon asymmetry problem. This discrepancy contradicts the concept of symmetric creation and raises questions about the conditions that led to the observed imbalance. The Sakharov conditions, proposed by Russian physicist Andrei Sakharov, provide a framework for explaining this asymmetry. These conditions are: there must be processes that violate the conservation of baryon numbers, allowing for the creation or destruction of baryons, violation of the combined symmetry of charge conjugation C, and parity P, as well as violation of the combined CP symmetry, where C is the transformation of particles to antiparticles, and P is spatial inversion. The universe must be out of thermodynamic equilibrium during the relevant times when baryon asymmetry is generated. Several theoretical mechanisms have been proposed. Some of the proposed mechanisms include electroweak baryogenesis. In this scenario, baryon asymmetry arises during the electroweak phase transition. Leptogenesis. This idea connects the generation of baryon asymmetry to the decays of heavy neutrinos, which are beyond the particles included in the standard model. The asymmetry is then transferred from the neutrino sector to the baryon sector. Gut baryogenesis. Grand Unified Theories, GUTS, propose a unified framework for particle interactions at very high energies. Baryon asymmetry could be generated during phase transitions associated with GUTS. Despite these theoretical proposals, explaining the observed baryon asymmetry remains an open question in particle physics and cosmology. Researchers continue to explore new ideas and conduct experiments, including those at high-energy particle colliders, to shed light on the elusive origins of this asymmetry in the universe. The quark epoch came to an end approximately at 10 to the power of 5 seconds. Following this, we transitioned into the hadron epoch, lasting from approximately 10 to the power of -5 seconds to 1 second after the Big Bang. This period was characterized by the formation of hadrons. A hadron is a type of subatomic particle that is made up of quarks. Initially, the universe consisted of a quark-gluon plasma, a state of matter where quarks and gluons are not confined within hadrons. As the universe cooled, the quark-gluon plasma transitioned into a state where hadrons, including baryons like protons and neutrons, could form. During the early stages, hadron and antihadron pairs could form, resulting in thermal equilibrium between matter and antimatter. As the temperature of the universe continued to decrease, the production of new hadron and antihadron pairs ceased. Consequently, most of the newly formed hadrons and antihadrons annihilated each other, producing pairs of high-energy photons. A small residue of hadrons persisted at about 1 second of cosmic time, marking the end of this epoch. The theoretical prediction of a neutron-proton ratio of about 1:6 initially decreases to 1:7 over time due to neutron decay. The remaining neutrons and protons participated in nucleosynthesis, where some protons and neutrons fused, giving rise to the formation of elements such as hydrogen, deuterium, helium, and other elements.